Hello there. Welcome to my stream. This is Kent Quirk. I am a programmer, have been for like 40 years now, and so what I'm doing here is I'm taking problems from Advent of Code, which is an annual 25-day fun puzzles for programming, typically computer science-y problems, and every day is a two-part puzzle, and what I'm doing is solving them live online while everybody watches. Well, or some sense of everybody's anyway. So please feel free to ask questions, say hi in the chat, and I look forward to tackling this problem and see what we can come up with. So, it's a rainy Saturday here, and it's blowing like crazy out there, so hopefully I won't lose my power, and it won't be too noisy in the background. But bear with me as we go, and let's get started. Oh, I guess I could actually show you my face. Hi. Alright. Sorry, I'm getting used to the streaming stuff, so it may be a challenge sometimes. But now we have started. So I'm going to share my screen and then show you guys what's up. So, first thing we have on the screen is up here in this window is my browser for Advent Code. Down here is the command line. It's what I was doing last night. I'm sharing all the stuff on GitHub. I am Kent Quirk on pretty much all the social media platforms. So on GitHub, on Instagram, on Twitter. I don't do Facebook though, so feel free to hit me up. And then this is my editor. Now one of the things I have to start off with is I need to create my workspace for today. So I'm going to close this version of the editor and I'll create a new directory for it. So now we're on day 5. So I'm going to clone my template repository. So if you don't know, in Z Shell and Bash, if you hit Control R, you can search your repository. You can search your history by just typing a few letters. So since I had done this copy command to day 4 yesterday, I hit Control R and I typed temp, and it found the most recent command that had temp in it, which is copy recursively the underscore template directory to day 4. This time we're going to do it to day 5. And now that gives me the directory I want, and then I'm just going to actually I'm going to cd into day 5 and bc dot. So there's Visual Studio now opened to that directory, and you'll see that what was in the template directory is just basically some empty files for my input files, and a template, a little basic main for Go and a little basic main for Python, to just read in those input files as text files, and then I can start to process them. So it just saves a little bit of boilerplate to get going. Pretty much every version of the project is going to need those. I also have a Go mod and Go sum file for, right now the Go mod is really basic, so we'll save that, but we aren't really going to need it unless I find some module that I actually want to incorporate. For today, we'll just go ahead with this. So let's read the problem, see what we have to deal with today. So it says day 5, binary boarding. Now the fiction here, the story we're developing is that we're going on vacation this year, and our problems have all been related to getting to or on a plane. Yesterday's was about boarding passes, and then today seems to be we lost the boarding pass. So let's see what's going on. You board your plane only to discover a new problem. You dropped your boarding pass. You aren't sure which seat is yours, and all the flight attendants are busy. You write a quick program to use your phone's camera to scan all the nearby boarding passes, which is your puzzle input. So they're going to give us basically these boarding passes, and we can try and find the seat through process of elimination. So basically by looking at all the seats and figure out what's not occupied. But instead of zones or group, this airline uses binary space partitioning to seat people. Okay. So could be a tree. A seat might be specified like FBF, BB, FFR, LR, where F means front, B means back, L means left, and R means right. The first 7 characters will either be F or B. These specify exactly one of the 128 rows in the plane. Number 0 through 127. Each letter tells you which half of the region a given seat is in. Start with the whole list of rows. First letter indicates whether you're in the front or the back. Next letter indicates which half of that region, etc., until you're left with exactly 1 row. So they give an example here. But this is just binary numbering. This is how binary numbering works. So literally our problem seems to be converting FBFB into 1010, or B means the upper half, rows 32. So it's F is 0, B is 1. And converting that to a number. So it's basically binary conversion. So, okay. And then the last 3 characters will be left or right. 1 of 8 columns of rows, also numbered 0 through 7. So again, L is lower half, R is upper half, and so L means 0, R means 1. And so we are, so FBFBFBF RLR reveals it as a seat at row 44, column 5. And to get the seat ID, multiply the row by 8 and then add the column. So that is also just treating this whole thing as a binary number where actually B and R are 1 and F and L are 0. And no. Yeah. Yeah. And then it's just an 8-bit or a 10-bit binary number. So this really seems like an easy problem. Let's just take a look at our puzzle input. It's just a whole lot of binary numbers, probably randomly sorted. Okay. Alright, so I'm going to start off by just copying those and pasting it into my input file. Oops, I didn't do that right. Do it again. Okay, there we go. And there are 933 of them. Okay, so there are possibly 1024 of them if there are 10 bits. So I'm going to save this. And from a sample point of view, like it's always nice to have some sample data that we don't have to go through 1,000 of them or print out 1,000 of them if we're just trying to debug code. So I usually do a sample file too. So I'm going to go back here, and they've given us, you know, a small set of samples. So let's just create 4 samples. All right, so there's a simple, easy sample file. So what is the highest seat ID in a boarding pass? So we need to convert these to a binary number. And I think we just do it the easiest way we can, which is what I was talking about before. B's and R's are 1s, F's and L's are 0s. And then we just convert it from binary to decimal. This is all right. So let's do this. If we look at the main Go file, so I've got some code here that reads the input file. We're just going to start with the input sample to make it easier, and this splits the input read on new lines. So we're going to get an array of strings, and just to prove that much works, we're going to just run this little source file here. So go run main.go, and there's our first thing. So great. And we need to convert this to binary. So I'm going to do, I'm going to create a function on day 05A, and it's going to take lines as an array of string, and okay, lines is an array of strings, and we're going to convert it to a binary number. Well, let's for underscore comma line colon equals range lines. So we're going to iterate over the full set of lines. Oh, what happened? I didn't see what happened there, but I made some glitch. Okay, so that's just going to iterate over the range lines. The underscore means that I'm throwing away the index variable, and line, is the content of the thing. And stop it! I'm getting phone calls. It's really annoying. So anyway, now we just have to convert it to binary. So let's write a binary conversion function. Takes S as a string and returns an int. And so there's a couple of different ways to do this. The sleazy way would be to actually just slap a 0b in front of, convert the string to a string of ones and zeros using text replace, and then slap a 0b in front of that, and then parse it with parseInt. Oh wait, actually I'm gonna look something up. Does parseInt, so parseInt takes a base, so I wouldn't even have to do conversion. I could just pass in 2 as the base, and return the binary value. And or you can prepend it with 0b and have that do it. But in this case, passing in a base 2, since I know it's a base 2, would be actually a useful way to go. The other way to do it is to just parse it manually by walking the string, looking up each character, and multiplying. Just because I think it's probably more instructive, I'm going to do it that way. I think from a practical point of view, the parse-int solution, it would be the fastest way to go. But let's just do it this fun way. So I'm going to do 4. We can be done with this now. So we can go, if we for in a string, we're walking those set of runes, which is what we want, but I don't remember whether there's an index for a for loop with strings. So just for fun and safety, I'm going to actually look that up. Golang string. So I'll say strings. Introduction to strings in blog. So I'm just looking up what happens when we go for a range loop decodes a rune on each iteration, and it is an index. Okay, I wasn't sure if the index was included in a range loop over a string. So for, I don't really care about the index. Or, actually the index, nah. We're going to just say, now we know that these strings are always 10 characters, so we could just, the easiest way is to, in that sense, is to loop forward through the string. But actually, in a conversion situation, sometimes it's just easiest to deal with the string however long it might be, and to iterate over the string backwards. So I'm actually going to do that here. So I'm going to go for, and we'll just do it with an integer index, and we can kind of, yeah, see, all right. I'm changing my mind because, all right, so strings are runes, and runes can vary in length. Now in this case, we think we have 1 byte runes because we have just capital letters in ASCII, so all the runes are single byte, and it's not a problem. But the way you're going to walk a string is by doing rune index, because Unicode needs to parse the string. So if you walk a string backwards by rune, every time you index, you have to walk the string from the beginning to find it. Or I guess there is a previous rune. Now I'm going to search a little more. Rune. Strings. So let's take a look at strings for a minute and just see what they have for iterating runes. Index rune, last index. Oh, I could convert the string to an array of rune and then walk that backwards. That's probably the right way to go. All right, I'm starting to decide whether it's worth doing the thing I'm talking about, which is actually just, convert. Like, the far easier way to go would be to to build a new replacer. So here's a thing. All right. Let's do this with string replacement because it's kind of fun to do that too, and it's another thing that people don't necessarily know about with Go. So I'm just going to do it this way. It's not that the other one's hard, it's just that it's tedious. And in this case, it seems like it might be the right way to go. So new replacer is, so rep colon equals strings dot new replacer. And we're going to look at the example. See, so basically what we're doing is making pairs of replacements. So we are going to say new replacer of F is lower, so F gets replaced with 0. B gets replaced with 1. Right or left gets replaced with 0. R gets replaced with 1. And that's our replacer. And then we can say bin gets rep dot, why is this not doing my Intel code? It's I'm going to quit my editor and open it again in hopes that Go Please works a little better this time. Oh, that's my problem. I shouldn't have put a curly brace here, and that's why I won't do anything. It's the one thing about Go Please is that, like, if what you have is syntactically incorrect before where you're typing, it probably won't give you any data. And bin is a keyword. So bstring equals rep dot, there we are, replace of s. And then I can convert that. So n comma here colon equals I guess we'll return an error from this function. Equals strconf dot parse int of bs2, and our bit size is 10. And it actually, in this case, the result must fit into a 10-bit value. Let's just say it fits into a 16-bit value. No, it's 10-bit. I mean, if we get a long string, that means it's just going to not give us the right answer. But, and then we're going to return in fact, oh, parse int returns an int 64, so I have to cast it to an int anyway. convert it to an int. In Go, it's conversion, not casting. And so I did that wrong. It's this. There, that's better. Okay. So I now have a function that converts that value to binary, and they're asking what's the greatest. So day 5a will just say max colon equals 0. Now I'm going to say n error colon equals convert to binary of line if error is not equal to nil, log that fatal, because if this fails, we don't care, we're just dying and walking away. And otherwise, if n is greater than max equals n, and so the thing is being asked to return, not return n, return max. And this is going to return an integer. There we go. So now here we'll say format that print line. Oh no, print it. We're going to do printf. Part A max value was %d \n day 05a of lines. Alright, so that's my part A, and we're going to try to run this. And we get a value out of range. Interesting. Oh, because, wait. Fitting into 10 bits. 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of curiosity, if I do base 11, does that work better? Ah, okay. Not base 11. So probably better off just saying, look, just give us a 32-bit value. And still 820. So the max value of our demo data is 820, and notice that the values were 357, 567, 119, and 820. So we got the right answer from our sample data. So now instead, we are going to try to do this with the non-sample data and see what value we get. Maximum value is 994, and that totally makes sense. We know that the maximum value it could be would be 1023, which is 2 to the 10th minus 1. And that would be, the text of that would be B, 7 B's followed by 3 R's. But that's apparently not in the data file. So let's put this number into the test, 994, and make sure that we got the right value. That is the right answer. So now let's figure out what they're going to do to us to screw us up for the second round. Ding! Alright, time to find your seat. It's completely full flight, so you should be the only missing boarding pass. However, some of the seats don't exist, so they'll be missing as well. So your seat wasn't at the very front or back, though. The seats with IDs +1 and -1 from yours will be in your list. So what is the ID of your seat? So what we have to do in this case, this is we're going to take all of the numbers we generated, convert them all to binary, sort them. So then we're going to find the maximum value is 994. So everything after 994 doesn't exist, and everything before some value won't exist. And then there's going to be a gap in the sequence. So we just have to find that gap. So basically, if we take the list that we have of ints and sort it, and then just walk the list until we find one value that is missing, then we're done. I am going to duplicate this function because it has some of the stuff we need, and do 5b. And instead of having a max here, we're going to create an array of ints to store these in. And then we will sort that. So seats gets excuse me, I'm sorry. Seats gets array seats becomes array of ints. And actually we're going to make it. So make array of ints, and we're going to give it a capacity of 0, and then we will append to the array using standard Go idiom, so that it's not any bigger than we ever need it to be. Now, one of the interesting things about Go is what happens is you make an array, you give it a capacity, and then if you use append, it will append within its capacity. So every array has both its current size and its capacity. So we can make an array that is actually has the capacity we need, but a smaller size. If you don't do that, if you give them if you just say make the smallest array, or make a, it'll give you like, I forget what the initial size is. I think if you don't say anything, it gives you like 8 items in the array. And then when you append, at some point there's no room to stick it in. So what it does is it doubles the array size and copies all the items over into it, and then reams your references into that new array. So what happens when you do that is every time the array is too small, you double its size. This is known as amortized constant time, because what happens is if each time you do it, it's going to be a like if you go double the size, then double the size again, then every time you double the size, it takes twice as long to get there. Then on average, the cost you pay for increasing the size of the array is a constant over the size of the array. And so that's a good technique. Now, actually what Go does internally, I've forgotten the exact numbers, but basically what happens is it doubles the size until you get to something like 1,000 items in the array, and then it increases it by like 25% each time. And again, don't quote me on the exact details, but it's something like that, because the idea is that you don't want to just massively increase your memory because you just went one bump over. So in that case, then it's not quite amortized constant time, but if it really mattered to you, you'd probably just figure out how to allocate it. So in this case, actually, one of the things we can do is, instead of making the generic array too small, we know it's going to be at least 512, and it's not going to be as big as 1024, so we'll take one doubling. So I think what I'm going to do is actually set the capacity of the array. So we're going to have 0 items in the array initially, but the capacity of the array will be 1024. It's small enough, I could do 512 and then double once, or I could do 1024, and we know it'll fit, and we'll never have to double it. This is a kind of it's a little optimization. It doesn't really matter. But, so we have seats. Now we convert the value to binary. We're going to die if something fails, but we know nothing's going to fail because we just did day 5a, and it works fine. So instead of comparing to max now, what we're going to do is we're going to take n, and we're just going to say seats equals append seats n. We're just going to append n to seats, which will increment the size of the array. And the other thing would be if actually, since we know how many lines are in the initial input, we could make the file, we could make the array to be the exact size we need. I just realized that. We know the size. I was basically operating on we know roughly how big it needs to be, so I'm actually going to fix this. Instead of using append, since we know the size we need, we can just do here, we can just say make this array length of lines big. And then we can just index it directly. So we can say, we can put an index in this loop. And we can say seats of I equals n. So now we have, at the end of this, we have the seats array is exactly the size we need it with every value filled in from the line string. So great, now we've got that. Now we have to sort it. So with Go, unlike a lot of programming languages, well, Go is introducing generics, so it doesn't have them yet. So when Go gets generics, then this kind of stuff will probably change. Go is close to getting generics, but at the moment, we don't have it. We're not working with generics. So instead, what we have to do is we have to use some clever tricks to deal with lists of things. Now, arrays of ints are common. Arrays of strings are common. So Go's sort facility actually supports the arrays of ints and arrays of strings directly, so it's pretty easy to deal with. So I'm just going to show you. So sort, and let's take a look at this sort. Package sort. So it's funny. Again, I've been working with a lot of programming languages. Go, most programming languages talk about arrays. Go talks about slices, and the reason is that slices are the way we generally deal with things. An array is specifically a chunk of memory with a contiguous set of values in it. A slice is like a view onto an array. So when you talk about slices, that means, the brackets don't have a number between them. So when we talk about, like, right here on line 24, that is a slice of string, not an array of string. If it's an array of string, it's going to say, like, 3 of one of string or whatever. So slices are a view onto an array, and you can have multiple slices onto the same array. And in any case, you almost always deal with slices in Go. You don't often have to think about the underlying arrays, but in some cases you will. In this case, we don't have to worry about it. So we're going to take a slice, we're going to pass a slice, we're going to manipulate a slice, and the make creates an array, but this seats as a slice on that array. So in this case, what we're going to do is we're going to sort this slice. So since we can just say sort dot ints of seats, and that will just sort that array. And that's easy. And now the second piece of this is, so the first element in that thing is going to be the first value in our structure, and and then we're just going to walk the array and we're going to look for a missing one. So let's create last is equal to the instead of calling it last, we're going to call it previous, and we're going to give it the value of lines, not lines, seats of 0 minus 1. Because what I'm going to do is I'm going to walk this array and I'm going to compare each element to its previous element and make sure the difference between them is 1. So this allows me to do that without a special condition in the loop for the first element. So previous is seats of 0 minus 1, and then for I colon equals range seats so we have an index I don't think we even need the index. So that, and then if prev plus 1 is not equal to seat, then we have found it. So basically, as soon as we come to the one that's missing, we're going to return it. And otherwise, we're going to return 0, and if we return 0, it's bad. So let's just print this. I see no errors, so I'm just going to try running this. We might be done. Part B, missing seed value was 61. That's kind of a low value, and I'm a little nervous about it. So I'm going to actually, just for fun, I'm going to format.println of seats, and I'm going to print from 0 to 10, print the first 10 seats and see what values we get. After sorting. Aha. See, my test. What did I do wrong on my test? Okay, so I said previous value is equal to the seats of 0 minus 1. And now the seat, this should be 61. Why isn't previous 60? Previous from 1 plus 1 is not equal to seat. Oh, I didn't update previous. I'm silly. That's my problem. I need to say that now previous is seat. That is my problem. So let's try it again. There we go. Seat 741. Alright, so I can eliminate this print statement now. Let's do it again. 741. So let's put 741 in here and submit it. And we did it. So, yay. I am going to check this in, commit the changes I made. We're going to skip, funny. I'm going to skip the Python. I'm going to add go mod go some, input text, input sample.text, main.go, and these two main.py files we don't need, and in fact I should probably just delete. So solve day 5 in Go. I'm not going to bother to implement the Python today. This is kind of trivial. There's 1,000 easy ways to do this. This wasn't actually a very hard problem. I'm hoping that these get a little more interesting as they go. But I think whoops, wrong. Yeah, that's what I was going to do. So what we did is we attacked the problem. The problem was trying to say, do you recognize binary numbers? Can you figure out how to convert binary numbers? They sort of were leading you into, well, make a list of seats and divide them in half and keep half and don't keep the other half and all that kind of stuff. But honestly, it boiled down to just convert it to a binary number and tell me what number it was. So we did that, and that gave us like a really simple way of solving this problem. So we just did that part. And I think it was fine. Part of the thing about advent code is if you don't necessarily see what they're looking for right away, you might run down some dark rabbit holes trying to figure out like some more interesting solution. Like if you didn't recognize that as a binary number, like I said, you would probably do something like make a list of the seats on the airplane and start doing essentially a binary search, like putting fence posts in, identifying the seats on the plane. And you could do that, but it's a little painful. Since we recognize that as a binary problem, easy enough to do. And I think we're good. So just to remind you, like I said, it says in my screen here at Kent Quirk on all the social media. Feel free to, contact me or whatever if you'd like. Give us a follow. Click on that follow button, and you'll hear about it when I go online. I am doing this at semi-random times every day until Christmas is the plan. Now, life happens, and I may not always be able to do it that day. So, if I miss one, since the way Advent code works, you can't skip ahead. You have to solve each problem in order. I will solve them in order, and maybe it'll leak past Christmas. I'm certainly probably not going to do this on Christmas Day, or I don't know, maybe I will. We'll see. Anyway, so that's it for today. Thanks for watching, and have a good weekend.